All right. First of all, I'd like to thank y'all for resisting the temptation to skip out on lunch or take a 2 o'clock flight. So it's good to see the numbers that are still here after lunch. I know these last days of the conference can be kind of interesting. It's unfortunate that Rob Thomas is not here, because what I'd like to do right now is I'd like to swear that I am not an infidel. I repeat, I am not an infidel. I do believe there is a real threat. I do believe that dead rats will be floating in your swimming pools, that there is an imminent mudslide waiting to happen. So the goal of this presentation is to provide some clarification on some of the mechanisms and some of the ways that those dead rats can end up in your swimming pool, and that the specific events that could trigger that mudslide. So by way of introduction, I am a security researcher in a small group in Austin. What I've been doing for the last several years is beating up on protocols, finding implementation flaws, finding bugs. So that's what I do for a living. I'm not someone out there who manages routers for a living. I beat up protocols for a living. So you'll see that perspective through this talk. So the goal of this talk is to provide some concrete data about vulnerabilities in BGP implementation. And what I mean by concrete data is I mean actual testing. Testing of routers, not theorizing about potential vulnerabilities in BGP or things that could happen, but real data. And the way that you do that is you get a bunch of routers in the lab, you write attack tools, you come up with a set of attacks, and you execute them, and then you come up with the findings. So in this talk, I'm going to give you a summary of the vulnerability testing we've done on a variety of implementations over the last few months. We'll plug those findings into an analysis of BGP best common practices, and the section on best common practices is many of the same things you've heard over and over again in this NANOG talk and in previous NANOG talks. But I'll factor in the difficulty required to conduct specific attacks and the sorts of access that are required to achieve that objective. And by way of caveat, I'd like to say up front that the focus of this presentation is actually on exploiting BGP, not on what you can do with a compromised router. So what are the actual risks if you try to attack a BGP process on a router on port 179? So if you look at the threat models that were outlined earlier this morning, a lot of this would fit into the packet injection or wiretapping that was on Steve's. And then I'll also provide some real-world data that can give us some clues on whether or not some of these best common practices in terms of locking down VTY access, SSH, HTTP, things like that, and also what is the behavior of BGP implementations out there in the wild. And there's some interesting comparisons between that behavior that we observed in the wild and what we observed in the lab. So I've got a lot of content, I need to move on. So as you well know, secure BGP, like secure DNS, has popped up on the radar of leading policymakers. Both of those protocols made it into the national strategy, and there's a lot of information out there about vulnerabilities in BGP and what can be done with BGP. Unfortunately, some of it does not seem to be based on any real empirical data, meaning it's not based on testing actual routers. So one of the goals of this presentation is to help clarify some of those issues. And another problem is that there are a lot of folks talking in sometimes vague terms about security holes or security vulnerabilities without specifically identifying what sorts of vulnerabilities those are. And that's another goal I attempt to address in this presentation. So, what do I mean by vulnerabilities? One of my pet peeves is people using the word vulnerability in a fuzzy way or not knowing what they're talking about. Typically, when I think about a vulnerability, there are basically three classes of vulnerabilities. You can have design vulnerabilities, And as you well know, TCP/IP by design has no security. You can tear down TCP sessions by spoofing resets. BGP, as you well know, without some of the security enhancements, has no built-in security. So those are design vulnerabilities. Implementation vulnerabilities, on the other hand, are when a process or an application does not do what it's supposed to do. These are typically based on coding errors. And buffer overflows are probably the most common or the commonly reported form of implementation flaws. And another and probably perhaps the most important vulnerability would be misconfiguration. Default passwords of Cisco, inability to do any sort of ACLs, things like that. Those would be examples of misconfiguration vulnerabilities. And it's important to make this distinction because, and those of you that were at the security BOF last night found out that vulnerability disclosure and reporting and notification is a very interesting area with lots of issues. So whether or not you're talking about a design vulnerability or misconfiguration or an implementation vulnerability can make a difference in terms of notification and disclosure. And basically an upfront caveat is that I am not going to be disclosing any specific product vulnerabilities. I will be discussing in general terms some vulnerabilities that were discovered. I'm not going to name any vendors, and I'm not going to talk about any exploit codes. So don't raise your hand after this and say, hey, I'm from vendor A, did you test my product? Because I'm either going to have to lie or say no. I'm not sure which is worse. And another caveat is that we did, and I'll go into more detail in the presentation in a little bit, but we did generate a set of BGP test cases similar to those released by a group in Finland with the Proto Suite, and we have provided those to CERT. Okay, so what did we do with our testing? Basically, many of the apparent security problems in BGP are related to insecurity of TCP, lack of authentication, lack of access control, things like that. So we started out with TCP. If you're an attacker, the first thing you're going to go after, or at least one of the first things that I'm going to try to go after if I'm a remote attacker, is I want to see what I can do with that TCP stack on port 179. Another area of testing was to determine the robustness of common BGP implementations by sending various sorts of malformed messages. Then we also tested sections of the BGP attack tree that several of us developed last fall. This work is the culmination of an effort that started 8 or 9 months ago within Cisco to basically lay out a comprehensive and systematic set of attacks against BGP and to turn that into some actual lab testing that could be verified and that could be reproduced. So last fall, Sean Convery and I and Dave Cook developed the BGP attack tree, and I believe it's in draft status for RPSec, and it may have already expired. And then the third part of this was to basically look at administrative ports out there and look at the behavior of common BGP speakers out there on the internet. So I know Sue is going to talk about attack trees a little bit in the next talk, but basically the way that attack trees work is you come up with a set of goals that an attacker would attempt to achieve, compromise a process, gain unauthorized access, conduct a denial of service. Those are generally the sorts of generic things that you face with any protocol. So you come up with a set of goals, and then you break down and each of these goals into sub-goals as means of achieving the parent goal. So in the draft Convery BGP attack last fall, we came up with 3 categories of goals. First of all were the kind of lowest discrete goals that we had with BGP that we called atomic goals. Compromise, and that can mean a lot of different things, MD5 authentication, establish an unauthorized session, reset a BGP session, spoof a message, things like that. Then and then you use a combination of these atomic goals to carry out more sophisticated and complex attacks. And in order to conduct some of the atomic goals, as well as to conduct the attack scenarios, you use a variety of techniques that may have nothing to do with BGP. Compromising a router, a generic DOS attack that does not require anything to do with BGP, those are all examples of what we call supporting atomic goals. And if you're interested in this, see the draft. Okay, so in terms of the specific testing, what we did was we took the attack tree and we broke it out into specific attacks. And the tests from the attack tree are usually the lowest level leaves of the tree, so to speak. So we looked at what is the behavior of TCP and BGP connection establishment on a variety of routers. What is the susceptibility of common TCP resource exhaustion, aka SYN floods and other sorts of TCP resource exhaustion. We wrote some tools to see how easy it would be to, let's say, write a BGP MD5 cracker for BGP. Try some MD5 flooding, did some updated flooding, and I'll just add that the attacks listed in italics are ones that I had to put at the end of presentation. This was originally over 60 slides, and I had to move a lot of stuff to the end. Then the BGP route insertion via TCP hijacking. This is what the most people are talking about. Compromising a link or guessing the TCP sequence number and causing an update to malicious update to be sent. And then the malformed messages. So the goal of this testing was not, and I repeat, was not to do any sort of competitive security testing. Making marketing claims about the presence of other vendors' vulnerabilities is foolhardy at best, just as making claims about the absence of vulnerabilities in your products. So I'm not even going to go there with that. But the purpose was to get a sample of implementation behavior to determine the overall risks of some of these common attacks that have been discussed. And if you see little numbers in parentheses, that means the numbers of implementations that exhibited that behavior. Now, in some cases, I did not include that because there are some really smart people out there that can say, hey, I know what this implementation does, so I can start putting names on these test results. And then I will add that any sort of statistics, CPU utilization, or routing process utilization, or time for a process, a peer to come up or come down, they were not based on a real-life loaded network. There's a diagram in the back that shows our network that we used for testing. So your mileage may vary if this were conducted on a real network. So one of the limitations of some of the existing BGP security work, and in particular, there's a presentation that was at Black Hat in Seattle earlier this spring, and I believe it's going to show up at Black Hat again in Las Vegas, was that they really didn't release any BGP attack tools. So we wrote some BGP attack tools with the goal of validating these tests. We also used a variety of commonly available open source tools, Nemesis, HPing, things like that. And then we wrote a really crude proof of concept BGP hijacking tool just to validate that behavior. Things like DSNF, you've probably heard of these. And then we also wrote a fuzzing package to basically generate the malformed BGP messages. Now, some of these tools we would like to put in the hands of responsible folks. Some of them, there's no way that we're going to do that. But email me, tell me what you do. The goal of this is to basically, put a stake in the ground and saying, here's some tests. We didn't test all the implementations. Folks need to start doing some more testing. So that's something I'll discuss at the end of maybe a good way to distribute tools and test procedures responsibly. So some folks may be wondering, why do you start out with these kind of boring tests up front? Why don't you go immediately to session hijacking or man in the middle, things like that? Typically, when I go after a protocol, you start with the viewpoint of a remote blind attacker that knows nothing about the target, and you determine what that attacker can do. And then you progress to an increasingly more knowledgeable attacker who knows information about the configuration, who the peers are. So you start from the best case scenario and move to increasingly worst case scenarios to see how things stack up. And depending on the level of how far you can get into the session, that determines the susceptibility to certain types of attacks, including TCP resource exhaustion attacks, as well as possibly some malformed messages. So one of the interesting things that I used to do security testing for Cisco. Now I'm in a research group, and other folks do that sort of product testing. But at most, I would get exposed to maybe 1 or 2 implementations of, let's say, IPsec or IKE or something like that. But this was very interesting because I saw 7 different implementations, and there was a great variety of behavior in terms of how these implementations responded to different messages. So if we start out the worst case, with sending a SYN from a non-configured peer, meaning you have not configured a peering session, and look at what the response is to sending that SYN. One of the implementations did what probably I would consider the best thing: silently drop. 3 of them sent a reset ACK. That's okay. Several of the implementations also SYN-ACKed. So those implementations that SYN-ACKed, you could use traditional, port scanning tools to determine BGP speakers. Now, if you spoof a SYN from an established peer, and there is already, and by established peer I mean there's a peer that's configured and the session is active, the behavior is as follows. Most of the implementations send a reset ACK, and that's the good thing to do. A few of them happily SYN-ACKed, so that leads to some exposures that I'll talk about a little bit later. Now, if we send a BGP open from a non-configured peer, most of them reset the session immediately. That's a good thing. Silently reset. We don't even, you cannot use that to gain any information. One of the implementations sent an open message with an authentication failure. Now, the rest of these, you are sending a connection from a configured peer with an invalid AS, and there are basically 2 different possibilities. Two different possibilities there. Now, I'll add that these tests right here with the open assume that there was not a peering session established, because if there were a peering session established, you would get a reset ACK. Okay, some interesting things that I saw when looking at these implementations. Some of them had basically no delay at all, where I could just send open, and do some sort of flooding attack with BGP opens. Other of them would wait 60 seconds or several minutes before allowing me to send an open again. Though during this timeout period, basically I send an open and they send a reset back. So that has some implications. It made some testing difficult on our part when we were sending large numbers of invalid messages, but that does have some implications. Now, it's also important to notice that, and this should be obvious to most folks, but it's important to put down that none of these, there was no way to send any sort of, send an update if you did not have if you did not use it from a valid peer or with the valid autonomous system number. Okay, so TCP resource exhaustion are just common TCP attacks in flooding. And you may be wondering, well, why test this? This is about BGP. Well, what I found in testing of other TCP-based applications is that there is typically, it's hard to determine what's an application layer problem and what is a TCP problem, and that doing some of the NAPTHA style attacks, and that's in the references, basically conducting resource exhaustions attacks beyond the first SYN receive state, you can have some aberrant behavior or sometimes crash the application. So just for the sake of comprehensiveness and to see what would happen, we did the TCP resource exhaustion attack. And they're basically, you're trying to exhaust TCP at 3 different states. Now, it's important to distinguish that I'm not talking about link saturation, I'm not talking about filling up queues, I'm not talking about sending packets that get punted up to the CPU that cause problems that way. I'm talking very narrowly just about TCP. So if on the implementations that would happily SYN flood, or that would happily SYNAC, whether it was from a valid peer or not, we saw a 5 to 6 minute delay in establishment of the BGP session. So basically what we did was I start SYN flooding, clear the BGP session, wait for it to come back, so it could take 5 or 6 minutes. Now sometimes if we put access lists on the peer to prevent the peer being attacked from sending its connections to the other peer, the session would never get negotiated. So what we saw is that typically in order to do a successful SYN flood to prevent BGP sessions from being negotiated, you would have to attack both sides of the conversation, and you first would have to reset the session. And that's relatively hard to do. Now there are some issues, potential issues with implementations that happily SYNAC packets in terms of resource exhaustion past that SYN received state. So TCP sequence number attacks, tearing down sessions, are one of the the most common attacks mentioned. Like in Sandra Murphy's threat document, she talks about basically how any outsider can spoof a reset and tear down a peering session. Now, that's actually turns out to be harder, at least what we found, that it was harder than what some folks have thought. First of all, as you well know, default TCP behavior is to Okay, so TCP sequence number behavior of typically if you want to reset a session, you need to get the source ports, source destination port, get the source destination IP right, and the sequence number right. We wrote a little tool that did that, and as you can see, you could bring down the session. Now, this is some math that shows basically how difficult it is to conduct a blind spoof, assuming that you have a good sequence number randomization routine in your stack. So what we saw was that if you guessed the sequence number, or if you gained network access, meaning you were in line, you could obviously reset the session, and it would cause about a minute for it to be down. Now there are some research there that says it's easier to go after the initial sequence numbers, but what we saw was that in order to do that, you have to have a lot of SYNACs coming back to be able to characterize those initial sequence numbers that are generated. So basically what we saw is that it's harder to conduct TCP resets than some folks have claimed. And if you implement best common practices, they should be virtually impossible. Okay, TCP hijacking, this is what most folks have talked about. We wrote a little tool that allows you to send the update to the router, and this was just based on sniffing the traffic. It was written in libnet and libpcap, and you can see that it successfully inserts the update. ARP spoofing is also a means of basically taking over a peer, but you have to have local access to that segment in order to conduct those sorts of attacks. In terms of one of the sets of tests we did was to generate malformed messages, and that's commonly referred to as fuzzing, and that's one way of finding security vulnerabilities in products. It's probably not the best way. The best way would be to do a code review, but we didn't have the source to all the implementations we tested. So a lot of folks are using fuzzing to test implementations. So basically the way this works, there was originally a tool called ISIC. I don't know if any of you have heard of it, that it generates a lot of invalid packets. Now the problem with ISIC was that really smart or not so stupid implementations, if the first few bytes of the message, and I'm talking generically, not just about BGP here, but the first few bytes of the message, if they are not valid, typically the implementation will just drop them. So the goal of our tool was to basically embed those invalid messages deeper into the packet. And we generated about 800 test cases for the open to determine the susceptibility of these malformed messages. So this would be an example of a simple malformed open. And you can see that there's the valid 16 bytes of the marker up front, and I believe that the length is actually valid as well, but the type is not a valid BGP message. So in most cases, this should be dropped by the implementation. We did the same thing for the update. And basically our test results, especially if you compare these to the results from SNMP, these seem remarkably positive. One of the problems with SNMP is that you saw the same problems showing up in everybody's implementation. We didn't see that. The problems that we found were unique to the implementation. And out of 1,200 test cases, we only found four distinct flaws. And 3 of these flaws, you actually had to be a configured peer and know the valid AS to conduct that attack. So here are just some recommendations based on looking at all the implementations, and this is probably more appropriate for vendors. So what we did next was we took a threat, we looked at 3 different threat models, a blind attacker, a non-blind attacker, and a compromised router. I think it's made eminently clear that basically all bets are off if you compromise the router. Things get progressively better if you're just talking about a non-blind attacker, someone just gaining access to the wire, and then a remote blind attacker. Now, in terms of the best practices that we used to validate these tests, I'll just talk about the ones that we added, and those are in red. The rest of these are fairly well known. We added some layer 2 best practices, which are probably more appropriate for shared media environments. So applying the best practices, we found that if you apply the best practices, conducting the TCP attacks to exploit BGP are virtually impossible. You know, in security, you never say never, but they're virtually impossible. Non-blind attacks, if you don't apply the layer 2 best practices, you'll have some susceptibility. And once again, all bets are off with compromised router. So big surprise, compromised router is the worst case scenario. But compromised routers in and of themselves don't have anything to do with BGP. And I know this is kind of an exaggeration, but you don't hear many folks talking about replacing, you know, SMTP or HTTP just because folks are compromising web servers or mail servers. Now, this shouldn't be taken as a reason not to pursue secure protocols, and that's a bit of an oversimplification. But all of the attacks that we looked at did not, if you're just going to talk about attacks that use BGP, the range of attacks is significantly limited. Okay, so basically what we wanted to do was we wanted to look at our best practices actually being applied out there. We came up with a list of routers and we did very non-intrusive, we sent very non-intrusive probes, basically 4 SYNs, and within the SYN payload there was actually a message saying this is not malicious activity. It provided an email and said please contact us if you have any concerns or question about this. Now, interestingly enough, how many responses do you think we got after sending out this? No, we actually got 1 from a government agency. So we all, assuming we got a SYNAC from a port 179, what we did was we sent a valid formatted open to see what we got back. Now, here are the results. Basically, we discovered, you know, of our total number of routers, you know, 115,000, we found approximately 4,600 that SYNAC'd. We found 3,000 that reset. The vast majority have sent no response. Now, those could be filtered, or there could be firewalling or something like that. In terms of the BGP opens, I was quite surprised to see the large number of opens or notifications that were sent back, because this did not, because these were all from non-configured peers. These probes were sent from the Cisco DMZ. So these source IPs of our packets should not be peers. So we got a large number of BGP messages back. Now, on the right column there, basically that data shows the number of SYNACs we received from SSH, Telnet, and HTTP. And in total, we found of the 115,000 routers, and I'm using routers in quotation marks, 16,000 had some sort of administrative access. That's a problem. That points to that issue of compromised routers right there. And the total number was 14% of the routers had some sort of administrative access. On this next slide, I have some interesting country breakdown. And I guess old Europe gets the award for the best secured routers. So Spain, France, and Great Britain had the lowest percentage of routers that had admin access. So basically, in conclusion, this first bullet here should be no surprise. It's kind of common sense, but it was good to provide some real data to back this up. Compromised routers are the biggest problem. These remote blind attacks are, in our estimation, not the problem that some folks have made them out to be. Also, that if you apply best common practices, both for BGP and TCP in terms of access control lists, you can pretty much mitigate most of the TCP attacks, including SYN flooding and also injecting data. And kind of this last point here is, and this is kind of came to me after listening to Rob's very entertaining presentation last night at the BOF and also earlier. Attackers are lazy. Why do all this stuff using TCP sequence number attacks, having to guess all this stuff, or use ARP attacks or to compromise a local host when you can just own the box? And one more slide, and then I'll open up for interrogation. So basically, encourage folks to do testing of their products. Security testing is always a good thing. Implement BGP best common practices. This is beating a dead horse. And this, force folks to, be more specific when they're talking about BGP vulnerabilities, because it's not all or nothing, and it's maybe not as simple as folks would make it out to be. More testing is needed, and a combination of folks, whether it's researchers, customers, or vendors themselves, they all need to take part in the testing. Okay, now I'll open up to the queue that's forming.
That's cute. Quick question. When you were looking at fuzzing packets, injecting malformed updates, were you looking at specifically at one of the side effects, whether you could actually generate a notify message, or were you looking at whether the router crashed or whatnot? What we've seen is really interesting is playing with some of that, constructing messages that are subtly wrong, is that it is possible to construct messages which router A or vendor A will actually pass on to vendor B, which will then say bad, error parsed correctly, and then cause notify storms, in some cases even being a few ASs away, be able to cause different vendors to not be able to talk to each other well.
So basically, sending some sort of invalid update that gets propagated all along, right?
Transitively by some router vendor.
We actually were just looking at the first message, so we did the opens and then looking at the response to
I would encourage you to do a lot of work, and we could talk about this on the malformed updates, because I think that's a pretty big open vulnerability.
The
ability to cause notifies remotely, and it's happened at a NANOG, during a NANOG actually, when there was AS zero appeared in AS paths, and it prevented Bays and Cisco's from talking to each other about this.
Yeah, given the complexity of some of those message formats, there could be some issues.
I'm Steve Bellevin. Thank you very much for conducting these tests, especially after the SNMP ASN.1 stuff a year or so ago. It's very reassuring to hear that we don't have similar glaring vulnerabilities in BGP. I would add one caveat. If you have BGP sessions that are going more than one IP hop, and you've got IGP security problems, that means that attackers don't. It improves the odds for of staging a non-blind attack. So it should not be sanguine if you've got multi-hop BGP.
Yep, I agree totally.
And I guess I'll be last. I'm Sue Harrison. In this moment, I'll act as IDR co-chair. So one question I have that I'd like to know is, did you use the unconfigured option in the new finite state machine? Were these peers unconfigured? There are some things that allow non-configured peers. So did you restrict your research to configured peers?
It was just to configured peers.
Okay.
I'll be available offline if anybody wants to chat about this stuff. Thanks.